Hello everyone, welcome back to our engineering mechanics dynamics class. Today we're going to start a new chapter, chapter 13, kinetics of particle, that includes force and acceleration. In previous chapter 12, all the lectures that we had before today was the kinematics of particle, where we deal with the geometric aspect of the particle and the body, but we do not consider the force into analysis. But in this chapter, we're gonna take the force um, into our consideration, and we'll solve problems. How to solve problems considering force, external force that is acting on the body. Um, so let's start. Our today's learning objective is state the Newton's second law of motion, and then formulate equation of motion. Um, the second law of motion is we can apply, um, for example, in this trailer, the car is pulling. If we consider the friction acting, first, if you start the car, you need to overcome the friction that is acting on the tires here, and also there is air friction if you consider also that, and also there is a weight of those cars. So how much force you you need to pull that trailer forward. If you want to calculate that, you can apply kinetics. Kinetics of motion, and Newton's second law of motion comes into play for this application, this type of application. Another example of you see here, the players is throwing a ball towards another player. If you do a mathematical calculation of that, if you consider the environmental effect, for example, the air resistance, the dragging force of the earth, of the ball towards the ground, if you consider all those, how much force you need to put to the ball so that it reaches to the targeted person, and then also there is a gravitational force, air friction. So if you all consider all those, so air friction is kind of a opposite force, right? If you consider all those things, and if you consider all those things to solve a problem, then this is the application of kinematics of particle. So let's start our theory. First is stating the first law that we need, Newton's second law of motion. Newton's second law of motion. So basically, what Newton's second law of motion says, that if there is a external force acting on a body, on a particle, of course the force is not balanced, and that we did on statics, that all the summation of all force is zero. This is not the case, that there is unbalanced force acting on a body. The force will cause, if it's acting on the body, the force will cause an acceleration of that body, and then the acceleration is proportional. So the law says the acceleration, if we represent the acceleration by A, so this says its acceleration is proportional to the force that is applied. And to make the proportionality into an equation, you need a proportional constant. Here we'll apply the mass of the body where the force is acting upon, and if we define that by m, mass, then the equation, we can turn this into equation, force equals to mass into acceleration. So this is basically the Newton's second law of motion, and this equation is also called equation of motion. So equation of motion. So all those problem we will solve in this chapter. Considering the external force, we can apply the equation of motion. Newton also said, next we're gonna talk about gravitational attraction. Gravitational attraction. So what is gravitational attraction? Everything we throw upward, it's going downward towards the earth, because the earth is pulling us down. So this is the gravitational pull that earth has on any object, and that's why we can walk on the earth. And then if the gravitational pull is less, which is moon, you see the astronaut was moving in the sun, he was like kind of jumping, because the gravitational pull of moon on a man was lower than the earth. So this is an example. So the equation of gravitational pull is F equals to G m1 m2. So m1 m2 could be any particle, any two particle, which is m1 and m2. If there is any two particles, the gravitational pulling force between them is represented by F, and we're talking about only two particles, m1 and m2. It could be any person and earth. m1 could be one person and m2 could be earth. Then we'll get the attraction force between earth and that person. So r is the distance between the center of two particles. So the center of the person and the center of the earth is represented by this small r. What is G? G is the universal constant of gravitation, which is defined as 6.673 into 10 to the power negative 11 meter cube per kg second square. So this is the value of G. Okay, and then when we talk about any particle or any object or any human body close to the earth, this force F is defined by weight. The weight W, not mass, weight. And this weight, so if it's a force, we said force equals to ma, mass. So the mass of that particle, object, or person, and the acceleration, here we know it's defined by G, small g. It is the acceleration due to gravity. We know its value is 9.81 meter per second square. So this is the gravitational attraction. So now let's talk more about the equation of motion that we have just explained. The equation of motion may have a different form for different scenario. We just say the equation of motion is F equals to ma. Now by F we mean one force, right? So what if there is multiple force acting on a body, right? For example, if I have a particle here and there is lot of force acting on that body, F1, there is a pull F2, there is a weight F3. So how to deal with that scenario if we have a lot of force acting on a body? It's just simple. We'll just have the summation of forces equals to ma. The mass doesn't change. So we'll take all the summation instead of one force, summation of all the forces we have, and then the resultant force equals to mass into acceleration. So what if the resultant force equals to 0? Well, in that case, there will be no acceleration. This is called a static equilibrium. So now let's think of another scenario of that equation of motion. If we have a system of particles, meaning if we have more than one particle, if we have a big object, any particle, any body, any object is made of like 1,000 trillion billions of atoms. So if you take atoms as a particle, so the system of particle in our like a body is full of tiny lots of particles. And if we consider that, how do we consider into our motion of equation of motion? First, we have to assume that in a body, the force there could be external force, right? External forces on all particles on the body, and there's also internal forces the particle exerts on each other. So first thing, we'll assume that the internal forces, because it's each particle is exerting same amount of force to the next particle it has. So summation of, if we represent the internal forces as small f, so we can say summation of all internal forces. Here I means number of the particles. If there is a 20 million particles, I will represent from 1 to 20 million or so. So summation of all internal forces is 0. Because, like I said, the forces between particles are the same and opposite. So again, we will be left with the summation of external forces. If there is more than one force, this is the summation of force, and we'll have the summation of masses of each particles and acceleration of each particles. And again, if we take the sum of all the mass of those particles, then we can say the mass could be the sum of all mass of the particles. If we assume that there is 1m, so if it's a body, we know there is a center of mass, which can be represented by G. So if is the center of mass, we can take the acceleration of each particles combined to an acceleration from the center of mass that we just defined, and then we can derive that m acceleration g from the center of mass would be equals to of all the mass of each particles and the acceleration of each particles. And from these two equation, we can say summation of all external forces equals to mass, the entire mass of the body, and acceleration from to center of mass. So it goes back to the previous equation of motion that we had. Summation of force equals to mass into acceleration. It's almost the same equation for system of particles. So basically, for there's like a lot of particles, we just consider all those particles is one body, And once we assume that all the particles acts as a one big body, then it goes back to the previous equation that we had: summation of all forces equals to mass of the entire body, and then the about um, acceleration about the center of mass. So next, there is one more thing that we need to cover for today is how do we solve this problem that will be useful for solving problems. How do we define these forces to solve problems if it's not unidirectional? We know there's like different coordinate system: rectangular, polar, or cylindrical coordinate system. So today we're gonna just talk about the rectangular coordinate system. System. Let me revise this. Coordinate system. So let us draw a rectangular coordinate system. We know it consists of x, y, and z. So x, it could be your y, and this could be your z direction. So if a particle is moving, if any particle or any object is moving, so you have a particle here which is for example moving in a curved path, so we can resolve the problem in x, y, and z coordinate. So how we can formulate those equations? It's simple again. Summation. So we start with, let me choose a different color. We start with the equation that we had, basic equation of motion. Now we'll just add the three direction, right? Summation of forces in x direction plus summation of forces into y direction and summation of forces into z direction equals to mass, which is not a vector, and it will have, for the acceleration, it will also have the x, y, and z component. So ax in I, which is x direction, and vector j, ay into vector j plus a z vector k. So the acceleration will have a three directional component. I, j, k is the directional unit vector. So from this equation, we can also put ij here, I, j, k, because these are in that direction. These are directional force. So if we come from this equation, we can have three equations taking those I components together, j components together, and k components. So we'll have summation of fx equals to max. We know there was I on both sides, right? This one and that one. Since we don't have anything else, so we can just ignore these two, and we don't have to write anything other than the summation of fx equals to m acceleration component in x direction. Similarly, we will have the summation of fy equals to m y component of the acceleration, and summation of fz in z direction, all the forces component of all the forces in z direction will be equals to summation of mass multiplied by acceleration component in z direction. So these are the three formula equation that we'll have for rectangular coordinates. So next we're going to solve, next lecture we're going to solve problems on rectangular coordinates, and once we solve some problems we'll move to some other coordinate systems. But till then, thank you so much. See you in next class. Take care.